Hello everyone, I'm Ashwani Singh, and today I'm presenting ocean intelligence for the Indian coast. So in this, I'll be covering different aspects. Firstly, I'll be covering the biological, geological, and chemical aspects of Indian Ocean and ocean water to relate it with the fishes and modeling fisheries. Then second, we'll be covering the dark fleet detection and vast aspects of it and how it relates with maritime security and different fisheries domain. And we'll also be covering the seaweed farms, fishery farms, and fish farms, and how and what the need to map it. And we have a huge seaweed farms and aquaculture, but that is currently being unmapped. So, what's the need of it and how we can do it? And eventually, we'll be considering how many heat waves is being affecting all of this together and what can be done in this aspect. On the first page, we have these four critical blind spots that I have figured out during my research, which I will cover today. The first problem that I faced was where the fish are. So, like there have been currently there are days in which the fisheries is being forecasted, but I found out there are some limitations and they're not sufficient. So the first thing was it covers only surface and doesn't dig deep into the ocean to figure out where fisheries are, and sometimes it's inconsistent. And then the next question comes: who is fishing? This is a vast part of Indian Ocean and Indian maritime, which is being not covered properly. This is usually done using AIS, and majority of fishing and these activities are done by small fisher folks who don't have this big fleets to have an AIS system. This all major fishing part goes unnoticed. So, and the third part is what is being farmed. Here, I will be talking about the aquaculture, seaweed farms, fishing farms, and why India doesn't have any mapping of these seaweed farms and what can be improved? How can we map this thing? And in the fourth thing, how these things are being affected by the changing temperature and various climatic phenomena that have been happening throughout the decade. So, as I will come again with the same principle that we have been coming again and again throughout this session today, that we cannot manage what we cannot see. All these gaps covers what we cannot manage, and once we get all this data, we can manage these things. We get to better policy making and better managing of these critical aspects of Indian Ocean. So, covering first, most of these gaps I have figured it out for the Kongan Coast region. Why I have done so? Kongan Coast is one of the most important Indian coast. Indian coast. It contributes around 41% of Maharashtra's total GSDP, and it has more important ports like Mumbai and JNPA. Along with this, only Ratnagiri and Sindhudurg and Raigad, like coastal areas in the Konkan coast, supports around 4 lakh falls. And along with this, it has been observed that throughout the decade, the fisheries collection has been declined by 42% to different climatic actions and climatic reasons. And there is a need to study these changes that is currently being happening in the Konkan region. So I have focused my research on the different aspects on the Konkan region only for start. Let's come to the problem. What the problem here currently is? The first challenge that we are currently facing is there is very less amount of data which we can study and derive some results out of it. So, firstly, there is need to cover the ocean deeply, and there is more data out of it which can be used later by these few stakeholders. The first one are the future calls. If there are more data, then a better understanding of ocean can be done, and these information can be conveyed to the future folks in such a way that can be useful for them. For example, like vast amount of whistle falls go they on daily basis in the vast ocean and without any proper guidance where they need to go to find the fisheries. So once we have a proper data, we have proper map, then they have the proper guidance. They know where to exactly go. They can save fuel, they can save their time, and they can increase their profit in the same amount of time and effort. And then the coastal policy makers. These are people who make policy for the ocean. But what happens if they don't have data? They hallucinate. They can't make proper decisions. They can't take proper decisions because they don't know what is actually happening deep down in the ocean. So it helps them. And then maritime researchers. We as a researcher can't go to the oceans, get the sensor data, get data, and always we can't. Most of the aspect, like even I personally face also, like while covering this aspect, At multiple phases in my research, I faced that there was a data gap. I don't have data. I don't have data to validate my findings. So there is it helps them also. And overall, this all covers together to come to help improve economic sector. And why this is necessary? So the past few decades, we have been seeing decline in fisheries collection and other big problems, climatic problems such as floods and other aspects that is being seen more often than before, which creates a need. This creates a need. Like now, this is a time when we need to expand our knowledge of the ocean and the data collection in the ocean. So, what are the critical gaps I will be addressing here? I will be covering the illegal fishing. Like there has been a lot of illegal fishing that is being currently happening in the Indian coastal regions due to different reasons. And one of the main reasons is not proper monitoring. So I will cover that aspect also. And then this whole thing will also can help the government and policymakers. As I covered earlier, they will have more data. They can know take decisions with data which are backed by data and which are logical. And in the third aspect, I'm trying to take all this maritime domain search and everything from a reactive basis to proactive basis. Currently, what happens when something happens, government knows thing, get the data on it, and then they take action. But what happens if we have a data previously? We have data even before the things happen. Now we know what is going to happen. Now we can make policies, we can take decisions beforehand and stop calamities from happening or stop things that are not meant to be. The first aspect of this is the potential fishing zone. So in this, I have tried to make a model that can measure the potential fishing zones throughout the Indian Ocean region based on different climatic factors, biological factors, and geological factors. It is based on an equation in which we have to put multiple parameters, and it gives us a probability score, which eventually tells us like if we go in a, if we have a map of Indian Ocean, then by the score we can tell which region have how much fisheries and which species are there. So this it also covers few of the major aspects like oxygen minimum zones and about the food web and forecasting aspects also, which is currently being covered and has several limitations currently. So how this is being done? Let's cover the limitation first. So currently, the current systems only measure the surface data using satellite, which cover only 1 2 meters of the surface data, and they take only few parameters into account for the fisheries procrastination. That's the surface temperature and chlorophyll, which I will just be explaining why is not enough to cover the whole fisheries region, and there is a need of more in-depth analysis with more parameters to cover these things. So while solving this limitation, the first thing that came into my mind, like how can we solve this problem? So the first thing that I noticed was there's a lack of parameters. The first thing I got to do, I looked for more parameters, and I found some parameter which strongly affects the food availability, the biomass, or the fisheries biomass in an ocean region. And I try to take those parameters. Along with this, I even try to find ways in which we can go deep into the ocean, not just leveling surface. We can go deep into the ocean. I have taken a for our this modeling we have taken a depth of depth of 100 meters, and we have done it for 100 meters of depth, which tells a lot about then the steep setting surface. So what we have done, we have taken 5 parameters from Copernicus satellite data, which is very good source of data because they have satellite data. Along with this, they will have sensors and they mix both of the data and give a single data which is the complete score of those readings, mixing both satellite data and the actual sensors. So I've taken data like MPP, NO3, chlorophyll, temperature. I will give details a little more, and I've taken it for the 100 meter of depth, and I've used temperature group because what happens in ocean, things don't vary linearly with depth. They change drastically, and there's no particular order. For that, I've used trapezoidal rule for using the column. So these are the so what I've done. I have made a single equation which has multiple terms, particularly 4 terms, and they have different weightages. Firstly, I will cover the terms. The first one is thermostability index, stability curve. It tells about how fisheries depend on the temperature of ocean. Like if for a of ocean, if there's some temperature that is particularly good for a species, then I have normalized between a score of 0 to 1, and I've given a score 1 means that is highly suitable for the species, and that indicates if that region has those species. And similarly, I have done another parameter which is oxygen suitability, which indicates the availability of oxygen in those regions. These, yeah, and this also indicates if it's the score is 1, then the oxygen is suitable, and if the score is 0, then they are the oxygen minimum zones, and we can even call them those zones hypoxia. And then these are the two other parameters. Net parametric production. What is this? Net parametric production indicates the amount of nutrients available, nutrients, or you can say the food available for fishes in the ocean. This directly indicates how much fish can be there in a particular region. If a particular region has more amount of phytoplanktons, food, then directly indicates that more fishes will be there. It's not always true. There are some cases which I will cover where this is wrong, but this is one of the most important factor here, which indicates the amount of fisheries in ocean. Then we have nutrient gradients. Nutrient gradients indicate the amount of nutrient difference and nutrients present in the ocean region, and it helps to forecast, because if there are more nutrients in a region, that indicates in future there will be more NPP, net food for the fisheries. So we can forecast if a region has more nutrients now, then in a week or 2 weeks there will be more food and there will be more fishes. And these are the 4 parameters: temperature, oxygen, net parameter production, and nutrient gradients. And I've mixed 4 of them together in this equation. I have first normalized them using these formulas so that I get a score from 0 to 1 for all of these 4 parameters, because they have different dimensions. So we can just directly add them or make equation of them. So first I normalized them to get a single score between 0 to 1, and then I have used this, I have called it the physics composite suitability index. It gives a score between 0 to 1, and it exactly tells how much probability of finding fishes are there in the ocean in a particular place. It integrates, I have those all 4 parameters in this form. I have given NBT the highest weightage, because where there are food, there will be fishes. Then there is O2. This O2 is currently not present in the current ways which are being used for current forecasting, and which creates significant problems, which I will be covering later. And then NO3 is also not there in the current system. So I have treated these 2 also based on their weightage. Currently the weightage is static, but with time they plan to upgrade the system to move it to more dynamic equation, which will be varying throughout the region of oceans based on the specific location and geography. And this is again the why I've used the trapezoidal rule, because in ocean this with the value of this parameter doesn't change linearly with the depth. So we have to do a trapezoidal integration to get the changes at every depth properly. And using this, we have got a similar structure of species. Like we can just predict now at which level what species will be available in what quantity approximately, and in which time of the year. It helps in forecasting which species can be found in which season and at which time of the day or year. I have done it. I have taken a data of 1 year for 2025, and I have plotted it throughout the year, and which shows this result. It shows that the amount of fisheries in ocean in the coastal region was at peak in the winter and was at low position compared to winter in summer, which is even validated by the CMFRA report, which says the same thing. So we have even validated this using this CMFRA report. And these are some other readings also. It also indicates how oxygen starts improving as soon as the monsoon arrives, as more water fall inside the oceans, and it increases the oxygen values. From these results, we can explain even some of the natural phenomena that are currently being happening in the oceans. We have seen there is this long curve. Let me explain why there is a high curve of fisheries in winter. So the reason behind this, it is the winter doom, convecting mixing. So what happens in winters? In winters, the water on the top of the ocean becomes cool, and it sinks. And usually, what happens? Fishes are mostly on the top level of the surface of the water. They eat the nutrients and plants and everything, and it becomes less in nutrients. In winter, those less nutrient water become dense and cold, and they start sinking deep down in the ocean, and the nutrient-rich ocean water from the downside start coming upwards, which replaces the nutrients in the ocean at that time. You can see here, I have shown this into diagram also, how these nutrients less water is coming down and the nutrient rich water is coming upwards, which replaces the overall nutrient concentration in the ocean and which increases and keep the flow of fisheries there. But if we come to the summer, this thing doesn't happen. In summer, what happens? The weather is mostly warm. So the top surface water is mostly warm. It is light and warm. So it doesn't go down in mixes. So the nutrient can't come upside on the surface, and those regions becomes nutrient-less zones. So if there are no nutrients, there are no food, then there won't be any fishes. This creates the problem, and this is the reason why we are getting this graph high in winter bloom and low in fall. And one more thing, why I have taken oxygen into account in my equation, and why it is helpful, because the current measures don't have oxygen in their equation. What happens? There is an example of a case where there are regions which have nutrients, but there are cases when for some time, if fishes don't come to those regions, what happens? The bacteria present in those regions start decomposing those nutrients using aerobic respiration. And in aerobic respiration, they consume all the oxygen in those regions, and their region becomes oxygen minimum zones or hypoxia. If we see on the surface using temperature and chlorophyll ratings only, we will see that this region has the good temperature and the good nutrient, but there won't be any fishes because there is no oxygen for them. And if they can't breathe, there is no oxygen, then fishes won't come. So the earlier system fails in these specific cases where there are oxygen minimum zones, which is created due to aerobic respiration of decomposing the food by bacteria. But our model also measures the oxygen values, so it also tells the places or regions where these conditions are being happening, so that we can ignore those regions. And then in our research, we also found out that there was a stark relationship between the temperature and the net primary production, which indicates as soon as temperature increases, the primary production decreases, and the whole fisheries, which also explains why there is winter bloom and there is a fall, less amount of nutrients in fall, as there are high temperature, which indicates less food and then less fisheries. So, what to explain the whole structure of our model now? Firstly, for this, what I have done, I have taken data from the Copernicus website, and then I processed it, normalized the data to give me a single score, and then I have merged the single score using my equation to get the primary fishing suitability index, which eventually tells the probability of fisheries in a particular location. Then I have done it for a long region, like for this. This is a Colgan Coast region. I've done this for small region. For every point of hexagon, I have calculated the PHN score and I've plotted it here. This indicates the availability of fishes in those regions. This kind of plotted for all these regions with the same data from the same Copernicus website also. Using the SC grid, and the final output was a single map which just tells in a single look where we can get the fisheries, and we have done it for a daily basis. It gets data daily basis and plot this map on daily basis. So coming again to this, like how it is different from the current existing PFZ approach, it covers depth analysis of 100 meter, which is improved version of the earlier surface approach. Then it also explains the habitat suitability. Different parameters also indicates the different amount of species which can be found in a particular region based on the values of temperature and the oxygen. Then again, I have given the map. We have given the map of this region, which directly indicates and helps. And then we can even forecast this as we have taken the nutrients into account. So we can even tell like how the nutrients will be there, how the fishes will be there from 1 week from today or 2 weeks from today also. Okay, so this was all of the PFZ. Then now the second thing was the maritime security aspect, especially related with the AIS. This is one of the very important aspects of maritime. Like India has around 2.5 million kilometers square of vast maritime region. In this, most of the fleets that are there don't have AIS. There is no proper monitoring system for them, and they usually go unnoticed. They don't forecast. They don't give any signals, so we don't know about them. and due to which there is large amount of IU fishing, fisheries mismanagement, risk of maritime security, as any foreign fleets from other countries can visit our country without AS, and which creates the maritime security aspect. And then there is also a risk to resource sustainability, as there is no control on this dark fleet. They can do any amount of fisheries in any region, and we can't monitor it. So there is a need to have a system which don't completely depend on AIS, which goes far beyond AIS to measure these dark fleet. So this is just illustrative numbers, not in exact numbers, which proportionally indicates that if the fisheries indicates like there are nearly 5,000 fisheries fleets, then only 500 of them are having AIS, and that only amounts to 70% of total fleet, which indicates the majority of the fleets are going unnoticed, unmonitored, and can't be we can't take data from them, we can't monitor them, we can't control them, which creates a lot of uncertainty and things which can't be controlled and some random aspects. So what we plan to do for it, we are using a method that is being previously done by North Korea also, and they have validated it in their region, and which results are from there only. They are able to track 900 plus using IS, and there are more than 700 dark fleet signatures which they use to detect using SAR and VIRS, and totally mixing all these solutions, they were able to get around 3,000 fleets, which was at 99.8% precision, which is quite a good number. So, what was the solution? AIS is a basic technology where the fleets have to broadcast using radio signals at their location, about their details. But for those fleets which don't have AIS, we plan to use SAR. What SAR is? SAR are the satellites which send microwave signals or microwave signals or sonar signals, which directly comes down in the ocean region, and they get reflected back by the ocean back to the satellite, and they measure using that only. And what happens if there is any fleet or something, then that will be metallic or that will be a hard surface, and it will reflect more microwave readings, microwaves than the normal ocean water, which will eventually help us to know like there is something metallic, something hard in the ocean at a level. And then we are using VIRS. It is a visible infrared imaging radiometer suit. What it does is in night it measures the dark lights. Because usually what these dark fleets do, they use bright lights to detect to attract fishes. And it's the same thing. We can use these satellites to see these bright lights in the oceans, which confirms that there are fleets which are trying to capture fisheries, and there are fleets. And then the third is the optical imaging. We can use the satellite data, the visual data, to figure out if there are fleets or not. Any one of them alone is not enough for this purpose. We need a combination of all these three methodology, SAR, VRS, and optical. So we will be using SAR and then validating it using the VIRS, and then confirming it again with optical to confirm that there is a dark fleet in the ocean region. This is the idea, and these are the benefits and availability and the data diet with the AI. So this complete system of using multiple technologies like SAR, VIRS, and optical, we plan to monitor all the dark fleets that are being operating in the Indian Ocean region. And then this is the second problem. India ranks second globally for the world's largest aquaculture producer, but even after this, there is zero recorded area of aquaculture, seaweed farms, and anything like this. And this creates a large data gap and blindness for the policymakers, government, people who are doing these farms. So, what are the aspects of this? Firstly, this creates a problem in marine navigation, as the big fleets don't know where these farms are. So there are usual cases where they tend to destroy those farms. Then there is no proper monitoring and policy making, and then there are security concerns of operating these fish farms, and that is currently there. Why they are being unmapped? Why they are not being measured? Firstly, how foreign countries like China have done this. They have used monsoon, they have used satellite imagery to measure those things. But for us, it is quite difficult. We can't just do it directly because in our Indian coastal region, there are a lot of time when there are clouds, there's monsoon time, so there is no proper visuals from satellite, and then there is very high variability in ocean sometimes. So, if we use satellite data, and if the water is too turbid, there are too much amount of sediments in the water, then if we see from the satellite, it looks like a seaweed farm, and which creates cases of false positives and false negatives. Sometimes they get measured as seaweed farms, and sometimes the actual seaweed farms can't be measured due to this reason. And then the third part is India has mostly straight coastal lines. So these seaweed farms are fishing direct ocean currents, ocean waves directly, which eventually destroys them and makes it harder to monitor on daily basis. And the main problem of of this is like most of the seaweed farms that India has are very small in size, so they can't be figure we can't figure out from optical imagery. It's become difficult to know from an image only that if this is a farm or not. So coming to the function of it, we are trying to study the special geographical aspects of the Indian coastal regions apart from the apart from the foreign region. We are studying geography, how it affects these things, and then we are trying to use multiple year of data. We will be taking the images from multiple years, analyzing it over and over again to find out the patches that were consistently there in those regions, which eventually proves like, yeah, this the thing was there from large amount of time. For this also, we are trying to use SAR in optical. SAR use microwave readings, which which do have the effect of clouds on it. So it can measure even in monsoon times. And then we will also use optical imagery. Together, we'll mixing by mixing both of these, we will be getting an overall image how this seaweed farms look. And SR depends on wind speed, wave height, tide, and polarization. And these are the one aspect of things. And optical is independent of these things. They are not independent. They give their readings differently, which is easy to which makes it easier for us to mix them together and get to a confirmation, like if the result is actually a seaweed farm, fish farm or not. So this is still in progress. We are finalizing details of it. So what was the main thing, principle behind doing all this? It is to make the whole ocean intelligence from reactive to predictive. Currently, what happens? Currently, what happens? All the decisions, all the policies are being made once the things have been done, once the problem is being there. But using our forecasting, our technology, our modeling, we can forecast thing or to estimate the railings and how the marine ecosystem will change in future and can make policies for it beforehand. Thank you.